Welcome to The Explainer. Today, we're literally digging into the science that keeps our entire world standing. We're going to explore the ground right beneath our feet and the incredible engineering that stops our tallest buildings from sinking and our biggest bridges from sliding away.
So let's just jump right in. Have you ever stood next to a massive skyscraper or driven over a huge bridge and just wondered what is really holding all of that up? We see the steel, we see the concrete, but the real hero of the story? It's completely invisible, buried deep in the earth. And of course, we all know what happens when that invisible hero isn't up to the task. The Leaning Tower of Pisa? That's not bad architecture, nope. That's a failure of the ground underneath it. So what's the science behind getting it right? Well, the answer isn't on the surface. It's deep inside it. To really wrap our heads around this, we have to make a big mental shift. We've got to stop thinking of the ground as just, dirt. We need to see it for what it actually is, a complex, incredibly variable, and absolutely critical engineering material.
This right here is the absolute core idea of soil mechanics. I mean, it sounds so simple, right? Obvious even. But the implications are just profound. The safety, the success, the entire lifespan of almost everything we build hinges on understanding the earth it sits on. So the whole field that tackles this huge challenge is called geotechnical engineering. And a massive piece of that puzzle is the science we're digging into today, soil mechanics. It's all about using physics to predict how the ground is actually going to behave under the immense pressure of our modern world.
Okay, so here's the crucial thing to get. Not all soil is the same, not even close. Engineers start by splitting it into two big families, and they act completely differently. On one side, you have your coarse-grained soils, like sand and gravel. Think of them as gritty. Their strength comes from friction, all those little particles grinding and locking against each other. But on the other side, you've got fine-grained soils, like silt and clay. Their behavior is all about water and this kind of electrochemical stickiness between their teeny tiny microscopic particles. And this is where it gets really, really cool, because one super simple ingredient can completely change how a soil behaves, especially those fine-grained ones. And that one ingredient is water. This is just a brilliant way to see it. This concept is called the Atterberg Limits. Just watch how a clay soil can totally transform just by adding water. When it's dry, it's a hard, brittle solid. Add a little water, it becomes semi-solid. A little more, and it gets into this plastic state. You can mold it, just like modeling clay. And then finally, if you add enough water, it turns into a liquid that just flows on its own. And engineers have measured these changeover points with incredible precision. The most famous one is called the liquid limit. That's the exact moment, the exact water content, where a soil flips from being plastic to a liquid. And it's defined as the point where the soil has this tiny, almost non-existent internal resistance, what we call shear strength, of about 2.5 kilopascals. It's a hugely important number for any kind of design. So, knowing the soil type and knowing its relationship with water, that lets engineers figure out its single most important property, its strength. How much of a beating can it take before it just gives up? Now, when we talk about soil strength, we're not talking about crushing it. That's not how soil fails. It almost always fails in shear. The best way to think about it is like a deck of cards. It's really hard to crush a deck of cards, but it's super easy to slide the top half off the bottom half. That's shear. A landslide, the ground shifting under a foundation, it's the exact same idea. Shear strength is just the soil's ability to fight back against that sliding motion. And that resistance, that fight, it comes from two main places. First, there's friction. Just like when you rub your hands together. Those sand and gravel particles lock together and resist sliding past each other. The second source is cohesion, which you can just think of as the natural stickiness that holds tiny clay particles together. So gritty sands, they rely almost entirely on friction. But sticky clays get their strength from a mix of both. Okay, so that's the toolkit. Engineers can identify the soil type, they can understand its relationship with water, and they can calculate its shear strength. So what can they actually do with all that? How do they engineer the earth?
The answer is pretty much everything. They use this knowledge to design the perfect foundations for the right ground conditions, making sure our homes and offices are stable. They figure out how to dig tunnels that won't collapse, how to build massive dams that can hold back a river, and how to create highways that don't crack and sink after a few years. This invisible science is everywhere,
holding up the entire world we've built. So the next time you're in a tall building or maybe driving your car over a long bridge, just take a second. Remember that complex, carefully engineered material just a few feet beneath you. It's not just dirt, it's the foundation of everything, all held together by this amazing invisible science.